Okay, so let's use these postulates to derive an expression for time dilation. It is the measurement of time elapsed in different reference frames. So let's have a look here. A reminder, the two postulates are that the laws of physics are the same for all observers in all reference frames, no preferred reference frame. Big one, the speed of light in vacuum is the same in all reference frames, regardless of the motion of the observers or the source. So we're going to use that in our derivation. And what we're going to do is we're going to consider something called a light clock. So a light clock is basically a way of measuring time with a beam of light. So I have a source here, B, and it emits a pulse of light. And the light travels a distance d till it hits a mirror, and then it bounces back and it comes back. Okay, so we're going to measure the amount of time it takes the light to travel to the mirror and come back. And so that we're going to call that amount of time. So if it starts when the second hand is there and then it comes back, the amount of time, we're going to call that delta t naught. So it's the amount of time for event 1 is when it emits, bounces off the mirror. Event 2 is when it comes back to where it started. Okay? So how do we measure? So first thing we're going to do is find the time for the beam to return. Okay, and we're going to call that delta t naught. Okay, so let's use, to that end, let's use here, we're going to use the definition of speed, or at least of average speed, right? And so that is v is equal to delta x over delta t. Now, in our case, v is the speed of the light. How fast is the light traveling? Well, it travels at speed c. And delta x is the distance traveled by the light. So it travels a distance d to the mirror, and then it travels a distance d back. So delta x in this case is 2d. And the amount of time, we're calling it delta t naught. That's the time measured by the clock. You know, from the clock's point of view, how long does it take? All right, so let's solve that for delta t naught. So if I solve that for delta t naught, I have the expression that delta t naught is equal to 2d over the speed c. So that is our expression for the time it takes for the beam to go to the mirror and come back, right? And that's also known as the proper time, because that's the time where both events happen in the reference frame at the same location. So this is known as the proper time. Now, let's consider a situation where we're in a reference frame and we're moving sideways. We're moving with respect to the clock. So we're moving at speed v, let's say. We're moving at speed v, so let me add a little v here. So we're moving, at speed v relative to this. And so from our point of view, the clock, when the beam first leaves the clock, the mirror is moving to the right, and when the beam reaches the mirror, it's moved a certain distance. And when the beam reaches back to the mirror, to the original point, we've traveled a total distance. So we're going to call the amount of time measured in our frame, we're going to call it delta t. Okay, so the total time to go from here to here, we're going to call it delta t. And we're going to allow that to maybe be different than this time here. So here's the clock. It starts at that point, and at delta t later, the mirror, the light clock has moved a certain distance. And so the total distance will be the speed that we're moving relative to the clock times the total time. So this distance here is v delta t. So we want to find the time, right? So we want to find, in our case here, we're going to find the time. In this case, it's delta t, right? So if I start again with v equals delta x over delta t, right? And I want to replace everything here. So let's see. So v is still, the light is traveling at speed c again. So, in this reference frame, the light's traveling at speed c. And because of Einstein's postulate, it's also traveling at speed c in this direction. So you can see what's going to happen here, right? It's traveling at c here. It's traveling at c here. and it's traveling a longer distance in this case, so the time is going to end up being different. It's going to be weird. It's going to get weirder before it gets easier, guys. C is the speed, and delta x, well, it's going to be 2 times L, right? Because it travels a distance L here and distance L back, and divided by the total time delta t. So we need to calculate what L is. Okay, so let me zoom in here, and we're going to figure out this distance L. Well, we said earlier that the distance from here to here is v delta t, so that means this distance from here to here is v delta t over 2, right? That's half the distance. So we can, assuming that this is a right triangle, which it is, we can calculate L. It's going to be, using Pythagoras, it's going to be the square root of d squared plus v delta t over 2 squared. So we have an expression for L. And we can use that to figure everything out. So now that we have expression for L, I'm going to plug that into here, and we're going to do a little bit more algebra. So let's see. I have that C is equal to now 2L. It's going to be 2 times, I'm going to plug in for L, the square root of d squared plus, and then here we had v delta t over 2 squared, and that's divided by delta t. So we have an expression here, and we want to solve it for time, right? We want to find out what's the amount of time in the moving frame. So it's a little bit of algebra here, but it's not too bad. Let's move the 2 and the delta t over the left-hand side. So I end up with c delta t over 2 is equal to square root of d squared plus v delta t over 2 squared, right? All I did was move over that 2 and that delta t. Let's square both sides. So I end up with c delta t over 2 squared equals d squared plus v delta t over 2 squared, right? So the whole point of this is to solve for delta t. So let me move the delta t to the left-hand side, okay? And so I end up with c delta t over 2 squared. Now I'm going to move that expression with the other delta t over, so it's v delta t over 2 squared is equal to d squared, right? So what do we do next? Well, let's factor out delta t. Let's factor out a couple things from those two terms so we can isolate the delta t. So I'm actually going to factor out all this c delta t over t from both terms. So c delta t over 2 squared, factoring out from both those terms, so I end up with 1 minus v over c squared. So all I did was take c delta t over 2, and I want to factor it out from both these terms. And if you multiply it through, you'll see we get the same result here. So if I multiply this through here, I get that. So that's equal to d squared. Let's see here. I'm going to isolate delta t. So let's move everything to the right-hand side except that delta t. So I end up with delta t equals 2d over c squared. That comes from moving this c and the 2 over. And then it's all that's going to be divided by 1 minus v over c squared. Now let's take the square root of both sides, and I end up with delta t is equal to 2d over c all over the square root of 1 minus v over c squared. So I have one last step that I'd like to do, and that's recognizing that this here, that's what we found earlier. We found that delta t naught is 2d over c. So we're going to replace that with delta t naught, and that gives us our final form of this equation, which is that delta t is equal to delta t naught all over square root of 1 minus v over c squared. So look at this insanity. This equation says that for that light clock, the amount of time measured by the light clock differs from the amount of time measured in the moving frame, moving at a constant speed relative to the light clock, by this factor here. That is an unusual thing, and it should make you feel a little uncomfortable. And what we're going to do now is we're going to look at what does it mean. So real quick summary, we started with a light clock, and the two events are it emits a beam of light that bounces off the mirror, and the second event is it returns. We measure the amount of time that it took to do that, the time between those two events, and then we measure the time between those two events in a moving reference frame. And we found that the time measured in the two is different. Now, an important definition, we're calling the proper time is the time measured in the rest frame between two events at the same location. So in this frame here, in this light clock's reference frame, two events at the same location, event 1 and event 2, that's called the proper time. And this equation here sort of predicts the behavior between those two. So just a couple bookkeeping notes and a couple notes on notation. This unwieldy thing, we'll usually rewrite it. And this v over c, you notice that it's a ratio of the speed of the reference frame relative to the speed of light. This ratio shows up a lot in special relativity. So we are going to call it something. We're going to call it beta. And it's just a ratio of the speed to c. And it's basically beta is, it's a fraction of the speed of light, right? If beta is 0.5, that just means it's moving at 50% the speed of light. If it's 0.99, then it's moving at 0.99 the speed, 99% the speed of light. So we'll often replace v and c with v over c with beta. And this weird factor here of 1 over the square root of 1 minus beta squared shows up a lot in special relativity, so we're going to call it gamma, the gamma factor. This is something we'll be calculating quite a bit. So if I rewrite it that way, then the equation becomes the proper time is related to the time measured in a moving frame times this gamma factor. Okay? Real quick, gamma factor is 1 over 1 minus beta squared. And remember, beta is a fraction of the speed of light. So if you plug in beta is 0, you get 1, right? If you plug in beta is like, I don't know, 10,000 miles per second. That's still pretty slow compared to the speed of light. So it would be like this. It would still be about, gamma would still be 1. You'll notice that beta is close to 1 until you get to like a large percentage of, until you get beta, this fraction of the speed of light, gets large. Like when you're going at 20% the speed of light, then gamma ends up being a slightly bigger number. And yet, as beta gets closer and closer to the speed of light, gamma tends towards infinity, right? Because beta, as it gets closer and closer to the speed of light, as it tends to 1, this number gets smaller and gamma blows up. So this is one of the things, right? This sort of limits the maximum speed. Just here, our equations don't work if you're going faster than the speed of light. If beta, if I plug in a speed of 2c, I end up with a square root of negative number here and our equations fail. So the speed parameter, beta, can go from 0 to less than 1. If it hits 1, it's undefined. And if it goes past 1, it's an imaginary number. So this is sort of sets an upper limit on the speeds that we can describe with special relativity. Here's that gamma factor for a variety of speeds. So if I put beta is 0.14 or 14% the speed of light, or 42 million meters per second, that's a gamma of 1.01. And if I go to like 90% the speed of light, then gamma becomes a larger number. And you notice if I go to 99.4987% the speed of light, I end up with a gamma factor of 10. And look at that, as I get closer, if I just go a little bit faster, gamma keeps getting larger and larger and larger. So we're going to see what that means in a second. So let's start with a simple example here. Alec is traveling on a rocket going at 80% the speed of light. Right here, right? So Alec is going at 0.8 c. Okay, so Alec is traveling at 0.8 c and relative to Bibby on Earth. So Bibby's just sitting on Earth and watches Alec travel. Alec travel from Earth to Alpha Centauri? And Bibby says, oh, look at that. It took Alec 10 years to get there. Neat. So Bibby measured that it took 10 years. According to Alec, how long did it take to get there? Well, let's write down what we know. We know that Bibby measured delta t to be 10 years. Now, that is not the proper time. Remember, the proper time would be the amount of time that it took from Alec's point of view, because the two events are when Alec leaves Earth and when Alec arrives at Alpha Centauri, and those two events happen in the same location in Alec's frame. So we're trying to find, Bibby measured 10 years, so that's this is for Bibby here. What did Alec measure? So Alec would be delta t naught, right? And that's what we're trying to find. Well, beta is our speed factor, and it's 80% the speed of light, so we'll put it as 0.800. So, it's always a good idea to calculate gamma in these problems. So let's calculate gamma. So, calculations. So let's calculate gamma. Remember, gamma is 1 over the square root of 1 minus beta squared. When I plug in 0.8 for beta, I get that gamma is about 1.6666. We'll just keep some extra sig figs for now. That's the ratio. So now, to find the time, then remember delta t is equal to gamma delta t naught. So delta t naught will be delta t divided by gamma. So in other words, 10 years divided by 1.6666 off to infinity. And when you do that, you end up with 6 years. So, like, what the hell, right? Bibby measures that it takes Alec 10 years to get there. But from Alec's point of view, Alec looks at his watch, and Alec found that it only took him 6 years to get there. So that is very not intuitive, right? That is against your everyday intuition. So what is going on here? Is this just some made-up crap done with tricks with numbers, or is this a real thing that actually happens? Like, if we were to actually do this experiment, instead of just me drawing on an iPad here, would this happen? And we've done experiments. We haven't sent Alec to Alpha Centauri, but we've done experiments to see if clocks in different reference frames measure different amounts of time. And the first one experiment of it was the Heffel-Keating experiment in 1972. They flew atomic clocks in opposite directions around the world. They synced them up at first, and then they compared the differences between them. And the differences between them was the amount predicted by special relativity. It turns out, within experimental error, that they did differ by a small amount due to the differences in their motion. They also had to correct for gravitational changes. Turns out gravity affects it, and that's general relativity. We'll mention general relativity later on, but this is a real thing. This is not a made-up thing. This is a thing that can affect real clocks and affect the real passage of time. It's just that in order to measure it, you need to be going pretty fast to measure a large amount of it, right? You're usually not going at a fraction of the speed of light, so you're not going to notice it. Another set of evidence for that is cosmic rays that collide in the upper atmosphere create these particles called muons that have a very short half-life. They exist for 2.2 microseconds. So if there were no time dilation, then when the muons are created, they would decay before they reach the surface of the Earth on average, right? Mostly. But if you take into account time dilation, in other words, if the muon, when it's created, is going fast enough, its clock, or it perceives time to be going slower, will last longer before it decays. And when you compare the number of muons at the top of a mountain to the number of muons measured at the bottom of a mountain, the number that reaches the bottom of the mountain is consistent with what would be predicted due to time dilation. Time dilation predicts that there would be a different number of muons that arrive at the bottom than at the top. So there's a couple different forms of evidence to show that time dilation is a thing. Just quick reminder. What is the proper time? So I have a rocket ship here, and the rocket says that it took 10 hours to reach Saturn. And Earth says that it took the rocket 16 hours to reach Saturn. So which time of these two is the proper time? So remember, the proper time is two events at the same location in the reference frame of the object. So the event 1 is when the rocket is here, and event 2 is when the rocket is here. Those two events happen at the same location in the reference frame of the rocket. So the proper time is the time as measured by the rocket. Let's do another example with this here, right? So if I have here, how long, according to the rocket, does it take it to reach Neptune? Earth says that it takes the rocket 5.157 hours to reach Neptune, okay? And it's moving at, it looks like 80.88% the speed of light. So just as a reminder how you can do this, right? Let's calculate. So remember, beta is v over c, so in this case it's going to be 0.8088. And when I calculate gamma, remember gamma is 1 over 1 minus beta squared square rooted. When I calculate that, I get 1.70. All right? This here, remember, is the time in the Earth's frame. So the time in the Earth's frame is not the proper time, so it's 5.152 hours. So we can easily calculate the time using this equation here, right? The time according to the rocket ship. And it's always going to be less. So the rocket ship is going to be delta t over gamma, and we measure about 3.03 hours. Okay? So here's an example. Remember I mentioned these muons that are used to provide evidence for time dilation. So if the mean lifetime of a stationary muon is 2.2 microseconds, so on average the lifetime of a muon at rest is 2.2 microseconds. So that means that its lifetime in its frame, in its reference frame, will be 2.200 microseconds, right? If we measure, let's say we create some muons, or some muons are created at the top of the atmosphere, and we measure their lifetime to be 16.000 microseconds. So we measure their lifetime in our reference frame to be 16 microseconds, so a lot longer than they are when they are at rest. So if we measure that, if we measure the mean, if we know that the mean in their frame is 2.2 microseconds, but we measure it in our frame to be 16 microseconds, we can use that to find out how fast they're going, right? We just use that delta t equals delta t naught times gamma. So let's solve for gamma. So we get gamma is delta t over delta t naught, right? So I plug in 16 divided by 2.2, and I get, I'll keep some extra sig figs here, about 17.272727, and so on. So we want to find beta, right? That's that gamma factor. So what we have to do is we have to find out how fast it's going. So let's use this expression here, right? Gamma is equal to 1 over the square root of 1 minus beta squared. So let's invert this sucker. So I'm going to square both sides. So gamma squared equals 1 over 1 minus beta squared. Let's see, I'm going to invert both sides. So I have 1 over gamma squared equals 1 minus beta squared. We move the beta to the left. We move the gamma to the right. So what I have here, I have beta squared equals 1 minus 1 over gamma squared. So I have beta is equal to the square root of 1 minus 1 over gamma squared. So when I plug in gamma is 7.27272727, I get beta is 0.9905. So that means the muons are moving at 99.05% of the speed of light. AKA C. How cool is that? So here's a fun sort of, this is somewhat related to the twin paradox, which you may have heard of. We'll talk about the twin paradox a little bit later on. But we have a father, just some guy. He's 50 years old. Okay? And he's heard about special relativity. So he's like, oh, all right. So if I travel for 4 years at a very high speed, I'd like to travel so that I travel for 4 years total. So 4 years, 2 years out, 2 years back. So the total time is 4 years. So that I age 4 years. But my daughter, who was originally 30 years, will then be 75 years old. In other words, I will age 4 years and my daughter will age 44 years. How much fun would that be? All right, well, let's see. So he goes from 50 to 54. She goes from 30 to 74. So the time that passed for him, remember, it's the time, it's the two events is in his clock. 4 years passes for him. How much time passes for her? So we have delta t naught is 4 years, and we have delta t for the daughter. Delta t for the daughter, who stays on Earth behind, ages 44 years. So we can do that to find gamma, right? So we do delta t equals gamma delta t naught. So solve for gamma. It's equal to delta t over delta t naught. So that's a gamma of 11, right? So we find that gamma is 11, and we can invert this again. We just did it, so we won't do it in detail again, but 1 minus beta squared. When you invert that, you get that beta is equal to the square root of 1 minus 1 over gamma squared. When we calculate that, we get 0.99586. So in other words, if he wants to age 4 years while his daughter ages 44 years, he's got to travel at 99.586% the speed of light until he comes back. So, a lot of weirdness here. Time dilation. We will look at some of the other consequences. Your brain might be thinking about all the ways that this can't possibly be the case. And we will sort of investigate them one at a time. We'll look at things like distances and synchronous things happening simultaneously. And we'll look at energy considerations. We'll look at momentum and all this weird stuff. So there's more to come on unpacking the implications.